Hello, everyone. This is the first class of the Differentiable Manifolds course at IMPA. So today we will start a review of differentiable manifolds. So let's first recall the definitions, the basic definitions. So first of all, just to be on the same page, a topological space is a pair xt where T is it's what's called the topology on the space X. So X is a set, and T is a subset of subsets of X. So it's a subset of the parts of X, which includes the empty set and the set X itself. And it has the property that whenever you take a collection of sets in it, the union of all of these is still in T. And whenever you take a finite number of them, of these sets, the intersection is in T. So when you have such a T, T is called a topology on X, and the elements of T are called open sets. So often there's no ambiguity which one T is. In this case, T will be omitted from the notation. So we'll just say that X is a topological space when T is understood. Um, so now a topology is often generated by a base. So what is a base of the topology? A base is a subset of T, of the topology, with the property that for every open set, so for every V in T, there exists a collection of elements on the base such that V is the union of UI. I forgot to write that UI belongs to B. Um, so yeah, so that means every open set can be written as a union of sets from the base. Okay, so a topological space is called two-countable if T admits a countable base. So for example, if you consider Rn with the standard topology, it is two-countable. Because there is there is a countable base that's very easy to check. So if you just consider the set of all n-dimensional balls with rational radii and with rational centers, so that forms a base because any open set in Rn can be written as union of open balls like that. I should emphasize these are open balls. Okay. So one more definition, which I think most of you are probably familiar with. A topological space is said to be Hausdorff if every time you have two different points in X, there exist open sets U1 and U2 in the topology, such that one of the points is in U1, the other point is in U2, and these two sets don't intersect. So that's what a Hausdorff space is. And recall that two topological spaces are called homeomorphic if there exists continuous functions from one to the other and from the other to the one, so from x1 to x2 and x2 to x1, such that both compositions are the identity. So that means that there is a bijection from one to, there is a continuous bijection both ways. Okay, that's what it means for these two spaces to be homeomorphic. Okay, so now we can talk about what a manifold is, at least a topological manifold. So a topological manifold is a second countable Hausdorff topological space X such that every point is contained in an open set which is homeomorphic to an open set in Rn. Okay, so every point has a neighborhood which is homeomorphic to an open set in Rn. You can also say every point has a neighborhood which is homeomorphic to all of Rn. Doesn't matter very much. And yeah, just a couple of observations. The first one is that we always suppose that n does not depend on p, and we call n the dimension of x. We can actually prove, even if you don't suppose this, you can prove that this number n is a local invariant. So locally near p, it has to be the same n. This is something you can prove just using some basic algebraic topology. But let me just assume that it's always n. What you could potentially have a manifold with disconnected components, one of which has different each of which has different dimension. But I don't want to suppose I don't want to consider those cases in this class. I mean, almost always my manifolds will be connected. And if they are disconnected, I'll just assume they have the same dimension. And another observation that I should make is that some authors don't, some authors consider topological manifolds which are not second countable or Hausdorff, and they impose these two conditions afterwards to get some of the theorems. But I don't really want to talk about pathological examples in this class. So I'll just assume that all manifolds are second countable and Hausdorff from the beginning. Okay. So now we want to define what smooth manifolds are. So in order to do that, let's quickly recall some basic notation. So first of all, a chart is one of these homeomorphisms. So it's a homeomorphism from a neighborhood, an open set of X, to an open set of Rn. Okay, so that's what's called a chart. And an atlas is a collection of charts whose domains cover all of X. Okay, so that's what an atlas is. And the name, comes from maps. A chart, you think of it as just being a map. When you try to draw a map of the whole Earth, for example, you can't do a map that fills up the whole Earth. So the idea is that you consider maps of different parts of the Earth, and then when you put them all together, you have an atlas. I guess that's why they chose these interesting names. So we say that an atlas is CK, so a CK atlas, whenever you have the following condition. When two domains, UI and UJ, overlap, so when their intersection is different from the empty set, then when you take what's called the transition functions, so let me draw a picture here. So if this is my UI and this is my UJ, you have a phi I and then you have a phi j. And then on their intersection, you could actually look at the projection onto one of the RNs and onto the other one of the RNs. And then if you just look at the intersection, you can look at the composition that goes here. So this is phi j composed with phi I inverse. So that will be a map from an open set in Rn to an open set in Rn. And the condition is that this map is CK. So it has K smooth derivatives. Okay. And here my K can go from 1 all the way to infinity, and it could be equal to infinity. Okay. So so a CK atlas is called maximal if whenever you have a CK atlas which is bigger than it, so which contains it, it actually has to be equal. So you can't get any bigger. Okay, and a CK differential structure on X is just a choice of maximum atlas. And then notice that any CK atlas is always contained in a unique maximal CK atlas. So how do you see that? Well, if you're given any atlas, so the condition is that these transition functions are CK and that the domains cover the whole space. So if you have any such atlas, now we can consider all of the charts. You can consider a new atlas, which has the charts that are in the original atlas, and then all of the other charts which are CK compatible with all the charts in this atlas. So this will be your maximal CK atlas, compatible with this original one. Okay, so yeah, we can now say that a CK differential structure on your topological manifold is a choice of maximal atlas. Sorry, I already defined this here. What I meant to say is that now we define a manifold to be a pair X and A, where X is a topological manifold and A is a CK differential structure on X. Okay, and then it's pretty clear that you don't actually need a maximal atlas to get a manifold. So you can just take any CK atlas and then you consider the maximal atlas induced by CK atlas. So all you need to define a CK structure on a topological manifold is one atlas. So you need one chart for you need a collection of charts that covers the whole manifold such that the transition functions are all CK. Okay, so now we'll actually see that, at first you look at this and you're like, well, this could be really complicated. If you have studied a lot of analysis, you're used to thinking that, oh, there are C1 functions that are not C2, there are C2 functions that are not C3. So there could be a lot of complications in terms of the differentiability. And now I'm going to tell you that actually in the world of manifolds, of differentiable manifolds, they don't really exist. So if you take two CK manifolds, you say that a map between them is CL for any L less than or equal to K. If when you look at the charts, the map that you obtain is a CL map. So I mean, the manifolds don't even have to have the same dimension here. I mean, I assume that they do in this in what I wrote here, but they really don't. So yeah, so let me just say it again. So you have a map, you say it's CL, if for every point in the domain of the map, there exist charts near the point P and near its image, such that when you look at F composed with phi inverse on the one side and with C on the other side, this is a map from Rn to Rn if this map is CL. Okay, and the point is that because little l is less than or equal to K, this condition does not depend on the choice of charts. So if you change the chart, then we know that the transition functions are CK. So because K is bigger than or equal to L, this expression here will still be CL for new charts. Okay? So in particular, we say that two CK manifolds are CL diffeomorphic if there exist CL maps that go from one to the other and from the other to the one, whose composition is the identity in both directions. So that's what it means for them to be diffeomorphic. I mean, when I use the word diffeomorphic, I already kind of mean implicitly that L is bigger than or equal to 1. I mean, I guess here you could still, for this definition, you could consider the case L equals 0. But I won't say C0 diffeomorphic because that's just homeomorphic. Okay, and then it comes a nice theorem. And the theorem basically is what I just said a few minutes ago, that there is no complication in terms of differentiability, order differentiability for manifolds. So if you fix any k that's bigger than or equal to 1, then every CK manifold is CK diffeomorphic to a C infinity manifold. So in other words, if you have a CK atlas, you can find a CK diffeomorphism to another CK atlas where it could potentially, throw away some charts, but then you still end up with a C infinity atlas. So, and then the second part is that if two CK manifolds are CL diffeomorphic, where L is less than or equal to K, then they are CK diffeomorphic. So, in particular, this first construction is unique. So from the point of view of classification, it doesn't really matter if you consider a CK differential structure or a C infinity differential structure. They're the same. And in particular, it's not possible for a topological manifold to admit a CK differential structure and not a CL differential structure where K and L are different. Okay, so that means basically that there's no advantage in considering CK differential manifolds for K different from infinity. So that basically tells us that we can just only look at smooth manifolds. So C infinity manifolds, and we don't lose anything. I just want to make one point, which is that you have to assume that k is at least 1 for this to be true. In fact, there are examples of C0 manifolds or topological manifolds that don't admit differentiable structure. And there are examples of topological manifolds which admit more than one differentiable structure. So, basically there is definitely a break between C0 and C1, but then between C1 and C infinity, there is no break. By the way, the proof of this theorem, I'm not going to do, it's very technical, and I don't want to spend too much time on it. It's not particularly interesting, in my opinion, but you can read it in chapter 2 of Hirsch's book. It's related to some stuff that we'll talk about in the transversality chapter, but I don't really want to prove this here. So if you're interested, look up in the approximations part of the transversality chapter in Hirsch's book. So anyway, because of this theorem, I'll only really consider C infinity or smooth manifolds in this course. Yeah, it's just easier not to be talking about different CK manifolds and emphasize different Ks. Okay, so now I want to remind you about these really beautiful structures called partitions of unity. They are very beautiful and they are very, very useful. So we'll need them. So the idea of partitions of unity is that, well, we know that a manifold looks locally like Rn. So in each little, we have little Rn's around each point. And then the idea of partitions of unity is that somehow, if you can do things locally, you can use these partitions of unity to glue the whatever local pictures you have to get some kind of global picture. This is not always possible, but very, very often it is. So what are partitions of unity? So before I define what partitions of unity are, let me just remind you a few facts about open coverings. So an open covering of a space, I think, everyone knows what an open covering is. It's just a collection of open sets whose union is the whole set. So an open covering is called locally finite if for every p in X, P doesn't belong to UI except for a finite number of i's. Or in other words, P only belongs to a finite set of UIs. Okay? And an open covering, VJ, a different open covering, is said to be a refinement of the first open covering, UI, if for every J, there exists an I such that Vj is contained in UI. Okay, and finally, a topological space is called pair compact if any open covering admits a locally finite refinement. So that's a very, very important, very good concept. So that basically means, if you start with any crazy open covering, then you can always find a locally finite refinement. Okay, so that's a condition that doesn't always hold for topological spaces. There are pathological spaces that are not pair compact, but an exercise on the problem set is that every topological manifold is pair compact. And actually, it's much stronger than that. Every locally compact Hausdorff second countable topological space is pair compact. So you can prove that. Moreover, every open covering admits a countable locally finite refinement. So it's not only locally finite, but it's also countable. So that means that this J here is a countable set. Okay, so now I can define what partitions of unity are. So if I take M, a smooth manifold, and UI, an open covering, a partition of unity on M subordinate to this open covering is a collection of smooth functions. So Fj are smooth functions with values in R. And here I'm indexing the functions on a different set, such that the support of F, so the support, if you don't know, it's just a set of points where the function doesn't vanish. So this guy determines a locally finite refinement of the original open covering. Well, the other condition is that the functions are always greater than or equal to 0, so for every j, and the sum is identically equal to 1. And now notice what's interesting is this j here is in general an infinite set. It could even be a uncountable set for this definition. But because the the set of supports is a locally finite covering, that means that this sum for every p, it's always a finite sum. So this expression makes sense. So it's not, there's no convergence here. It just, this sum is a sum of, it's a finite sum for every p. So that makes sense. And the theorem, which is actually pretty amazing the first time you see it, is that given a smooth manifold in any open covering, there exists a countable partition of unity on M, which is subordinate to this open covering. Moreover, if the index set is countable, we can assume that I is equal to J, and that the support of each Fi is contained in Ui. Okay, so I mean, in particular, if you don't even care about open coverings to begin with, there always exists the partition of unity. So if you don't start with an interesting open covering, you can just take, for each point of the manifold, you can take a neighborhood of this point, and then that will give you an open covering, and you can apply this theorem like that. So again, this is just a review of manifolds, so I won't prove this. It's not very hard, but the main idea is to find a function, is to define bump functions. That's kind of the main analytical tool, and then you play some topology with balls of different sizes and getting bump functions that vanish on certain set outside of certain open sets. And yeah, so after this exercise, it's basically just an analysis exercise. Okay, so you can see any book about manifolds, in particular Lee's book. So if you don't know John Lee's book, it's a very good reference on manifolds. It's very detailed, so it might be hard to read from the beginning to the end, but I think it's a very good encyclopedia. Okay, so now let me talk about the tangent and the cotangent bundles. So again, this is a review, so I'm going to be a little bit quick. And if you haven't seen this before, you might want to pause the video and do it slowly, or read the material yourself. Okay, so let's start with a smooth manifold, and let's pick a point P on M. And we can define the tangent space, Tp of M, to be the set of curves from a little interval around 0, which are smooth, and such that gamma of 0 is P. And we quotient that by an equivalence relation, where the equivalence relation is the following. We say two curves, gamma 1 and gamma 2, are equivalent if for a given chart around P, we have that the composition of the chart with gamma 1, when you take the derivative of that at 0, you have the same derivative. So this makes sense because once you compose gamma 1 with the chart, this composition will be a map from R to Rn. Okay, so basically you look at curves that go through the point that have the same derivative at the same vector, tangent vector at the point P. So this is a kind of more concrete definition of the tangent space at the point P. And maybe if you've seen this before, which I think most of you have, you might have seen the definition a little bit more abstractly, which uses the following idea. So notice that if I have a vector, so an equivalence class of curves, it induces a derivation on the set of smooth curves. So derivation is just something that it's a functional that will on the set of smooth functions that will that has a Leibniz rule property. Okay, I'm not going to define what it is. I think you probably know, or you can look it up. And the way that you define it is v applied to f. So this is the directional derivative on f. So this is just you compose gamma with the function f, and you take the derivative at 0. So this composition is a function from, sorry, this is a function from minus epsilon to Rn, no, to R. So it has a derivative at 0. And it's easy to see that this does not depend on gamma. Okay, so if you change it by, if you change gamma, then this number is preserved. If you change gamma in the equivalence class. Okay, so an exercise is that so this gives a derivation, and an exercise that there's a bijection between this set of equivalence classes of curves and the set of derivations at P. Okay, so it's something that I think all of you who've taken a manifolds class have seen, and if you have not, I encourage you to think about this, because the language of derivations is much easier for abstract thinking, but it's a bit hard to visualize what's going on without this definition here. So a corollary is that, the set of derivations is very easily a vector space. So a corollary is that TPM admits a natural structure as of a vector space. Okay, so it's a little bit harder to see it using this definition, but you can still see it. And there is, given a chart, if you pick a chart around P, there is a natural basis of this vector space, and the basis is just given like this. So it's called, the elements of the basis are called del x1 up through del xn, and they're defined like this. Del xi applied to f is just you take the composition of f with the pre-image, with the inverse of the chart, and you take the ith partial derivative at xi with respect to xi at the point 0. Okay, so if in the, or another way is in terms of equivalence classes of curves, you can consider the following things. So you can consider the curve that is gamma I of t is phi inverse of 0, and then you can take t, and then you can take 0, where t goes in the ith coordinate. Okay, so you just look at the curve that travels along the ith coordinate and keeps all the other ones 0. Okay, and the equivalence class of this curve is this element of the basis. Okay, so now you can consider this joint union of all of these vector spaces for all the p's, and that's called the tangent bundle, or the tangent space. And we'll see that it's actually a vector bundle. So, well, in principle, we can just take this joint union like that, and we have this map pi that that's just a projection onto P. And you can use the pi to topologize Tm if you want. So, you can consider the smallest topology, the topology that makes this map pi continuous. Okay, the induced topology by this map. Sorry, not the smallest topology, but the induced topology, given considering that these guys, the open sets also they come from the open sets in TPM. Okay, so another way to do it is you can say that given a chart um, phi, this induces a chart phi tilde from the pre-image of U to Rn times Rn. And you can actually use these phi tildes to topologize TM if you want. But more than topologizing TM, you can actually use these guys to define a topological manifold and a smooth manifold structure. So if you just take smooth charts, then these phi tildes will give rise to an atlas, a smooth atlas on TM. And what's the smooth atlas? Well, given a vector, so given something in the pre-image of U, what is that? So we can write that as the sum of vi ddxi at the point Q. So Q is where you are in U. And then you can take this vector to, well, the first Rn is just the image of Q by the chart. And the second Rn is these numbers vi. Okay, so this collection of charts will will induce a smooth manifold structure on TM of dimension 2n. Okay, so TM is a manifold. Okay, next time we'll talk about vector bundles, and we'll see that basically this is a vector bundle. But now I just wanted to say that it's a manifold. And then we can also talk about the cotangent vector space. So that's just the dual of TPM. Okay, so the dual just means that this is a set of linear maps from TPM to R, if you don't remember your linear algebra. Okay, so how do we get a basis for it? Well, given a chart around P, it's not very hard to see that it induces a basis, dx1 through dxn. So this is just the name that we give of TP star M. And what is this dxi? So what does it do to a vector? How does it eat a vector? Well, it's just the following. You have to consider v apply to some function. And the idea is just to use the function xi. But xi is a function that's only defined locally near p. So xi is only defined in u. So before doing that, you multiply xi by a bump function, which whose support is inside of u, and that is identically equal to 1 near p. And then you extend this to all of m. So you can think of this phi times xi. You can extend this to all of m. Okay, so then that makes sense. But anyway, this is just the derivative of the directional derivative of the coordinate function xi in the direction of phi. So that's what this is. And then an exercise, which if you haven't done this, you really should do, is that this dx1 through dxn is the dual basis of del del xi through del del xn. So dual basis just means that whenever you take an element here and you apply to an element of the basis, this is going to give you 0 if it's not the same index, and 1 if it's the same index. Okay, so this means that dxi p applied to del xj p is the Kroneker's delta. Okay, so finally, we can define T star of M to be the union. Well, we can write like the other one, disjoint union of TP star of M. And again, similarly to TPM, to TM, T star M has an induced structure of a 2n dimensional manifold. And one more thing I want to say is, so this is sort of an example is about the differential. So if you have a function on say infinity of m, we can define dfp, which is a cotangent vector um, at tp star m. And this is very simple. This is just when you do this, if x is a vector, if x is in TPM, dfp of x is just the directional derivative of x in the direction of f. Sorry, the directional derivative of f in the direction of x. Okay, so it's x applied to f. And if you look in terms of the basis, so if we fix, if we choose a chart, this guy is actually equal to the sum of df dxi dxi p, where df dxi, this guy here, is just you write f composed with phi inverse, and then now you can take d dxi at the point 0. Okay, so this kind of explains why we use this notation of the differential, and also explains, why we wrote dx1 through dxn. Okay, so because today, I guess the material is kind of dense, I'm gonna stop here. It's a little bit shorter than an hour, but I think we have enough material for today.